Hi folks, Morgan back at you with some more calorimetry problems. And question number 3 that we're going to be talking about right now is one that is a very typical scenario that would be run in an industrial process. Checking to see what type of final temperatures would be achieved in a reaction tells people whether they need to, run something in a cooling bath or in a heating bath, what type of vessel it has to be run in, etc., etc. Okay? So, what we have, again, is a nice styrofoam cup. It's got some water in it. We're dropping in a piece of aluminum. And we're going to calculate what the final temperature is. To a calorimeter, heat capacity provided, containing 100 grams of water at 25 degrees Celsius, is added 50 grams of aluminum, heat capacity provided at 100 degrees Celsius. What is its final temperature? Now, here I think we can just pretty normally say that Q total equals 0, which equals Q that the aluminum lost plus Q that the water gained plus Q that the calorimeter gained. And we'll have a little bit more of algebraic stuff to do this time, but it's not going to be impossible. 0 equals, now the mass of the aluminum is 50.0 grams times the heat of the heat capacity, of the aluminum. We don't know the final temperature, so we're going to call it T final. Okay? Minus its initial temperature, which was 100.0 degrees Celsius. Plus, now for the water, we have 100 grams times 4.184 joules per gram degree times a temperature change of T final minus, and that is starting out at 25 degrees Celsius. Plus then for the calorimeter itself, 195 joules per degree times T final minus is going to end at 25 degrees Celsius. It'll be in thermal equilibrium. Okay, so equals this times this times this is 45 joules per degree Celsius T final minus, and then when we do this next term, the degrees Celsius cancels out and we get 4,500 joules plus this times that, which gives you 418.4 joules per degree Celsius T final minus, and this times that gives you a whopping 10,460 joules. Plus, this times this is 195 joules per degree T final minus 4,875, that times 25 joules. Now, in algebra, what I'm going to do that's a 0. In algebra, what I'm going to do would be called group-like terms. 45 joules per degree, T final, plus 418.4 joules per degree Celsius, T final, plus 195 joules per degree, T final, equals, and on the other side, these negatives will move over, and I get 4,500 joules plus 10,460 joules plus 4,875 joules. So what I'm ending up with is, adding those together, 6 joules per degree times T final equals 19,835 joules. So then I can divide both sides of this by 658.4 joules per degree Celsius, 658.4 joules per degree Celsius. 658 cancels, those units cancel, I'm left with T final. Joules cancels, degrees Celsius makes its way upstairs, and this is right in the neighborhood of 30 degrees Celsius. Okay? Now, that's a pretty straightforward question with a lot of algebra. Just a lot of this arithmetic that you're working through here. But there's only one unknown, so it's not a system of equations or anything like that. It's just in your math classes, we typically don't teach you to solve things that are that big and complicated. Okay, I'd like you to pause the video, go, and try and do number 4 on your own. Okay, I assume you are tuning back in because you finished the problem. So I've got my calorimeter with water. I'm dropping in a chunk of aluminum. I've got all my relevant numbers that are given here. Okay? Q total equals 0. I love the first law of thermodynamics. It's wonderful. Which equals Q that the aluminum lost plus Q that the water gained plus Q for the calorimeter, which also gained, which equals. Now I am once again looking for a final temperature. So the aluminum, as you read through it, you find out that there were 100 grams of aluminum times a heat capacity of 0.900 joules per gram degree times T final minus, and it started this time at 95 degrees Celsius. That number eventually is going to turn out to be negative. That's great. That means heat lost. Plus, now for the water. I've got more water this time, okay? This time I got 200 milliliters, which is the equivalent of saying 200 grams times 4.184 joules per gram degree times T final minus, and we're starting at 22 degrees Celsius. Plus, now, the calorimeter itself, okay, has a heat capacity of 50 joules per degree times T final minus 22 degrees Celsius. Okay. 0 equals this times this times this, then this times that. Okay, I am distributing 90 joules per degree T final minus 8,550 joules. A little dyslexia there. 836.8 joules per degree Celsius T final minus 18,409.6 joules plus 50 joules per degree T final minus 1,100 joules. So when I group my like terms, what I end up with, and I'm going to factor some stuff out here at the same time, 90 plus 836.8 plus 50, all measured in joules per degree Celsius times T final, equals 8550 plus 18,409.6 plus 1,100 joules. Okay, so dividing both sides to solve for T final, okay, I have 976.8 joules per degree Celsius times T final equals 28059.6 joules. I can divide both sides by 976.8 joules per degree Celsius 976.8 joules per degree Celsius. That cancels. Those cancels. Joules cancels. And T final equals about 28.7 degrees Celsius. Okay. So what I'm going to do is I'm going to leave that on screen here. Pause if you have to. I'll count to 5. I'll go back to the first one, leave that on screen. Pause if you have to. Okay, and those are some pretty typical calorimetry questions for you. Okay, I hope you did well on that problem, and we'll be talking about bond enthalpies next. Everybody have a good day.